Okay, this is problem 10 of the AMC 10A. Daniel finds a rectangular index card and measures its diagonal to be 8 centimeters. Daniel then cuts out equal squares of side 1 centimeter at two opposite corners of the index card and measures the distance between the two closest vertices of these squares to be 4√2 centimeters, as shown below. What is the area of the original index card? Okay. Well, there are two variables that we need to keep in mind here. One is the length of the index card, one is the width. Let's call them A and B. Let's call this, that'll be A. Let's call this B. Okay, well, what does this 8 mean then? Well, 8, that's the full diagonal, right? Well, by the Pythagorean theorem, that means that A squared plus B squared is equal to 8 squared, which is 64. Okay. Well, now the harder question, what exactly does this 4√2 mean? Well, if you think about it, because this is a rectangle and this is like little squares, right? Everything is right angles. And the good thing about right angles is we can shift things down. So basically, we can shift things across and preserve their length because of rectangles having opposite sides the same length. So for example, here, if we make this, if we draw this extension here, these are all right angles. This is a rectangle. So since this length we know to be 1, this is also 1. And this is 1, which means that this is just A minus 2. And we follow the exact same set of, the exact same steps to get that this length here, right? This length, like this length here is B minus 2. And this, and this length here is A minus 2, right? So disregarding those edges, right? So basically what that tells us is by the Pythagorean theorem, A minus 2 squared plus B minus 2 squared is equal to 4√2 squared, which is 32. Well, now we have enough information to solve the problem, right? Because we have two variables and two equations. We can solve for A and B. So let's do that. But we'll go about it in a way where we don't even solve for A and B. Let's just solve for the product AB. We don't need to solve for it. And what I mean by that is we're going to expand this. A squared minus 4A plus 4 plus B squared minus 4B plus 4 is equal to 32. And that means, well, this A squared and this plus B squared gives us a 64 in the equation, right? Because A squared plus B squared is equal to 64. And then minus 4A minus 4B is equal to 32 minus 4 minus 4, because we're subtracting both 4's, 24. And now that just gives us that 40 is equal to 4A plus 4B, which means that 10 is equal to A plus B. And now we can go back to this equation combined with this equation, because if we square this equation, we get A squared plus B squared plus 2AB is equal to 100. But A squared plus B squared is 64. So if we subtract the two equations, 2AB is just 36, and AB is equal to 18. And if you look back at what the problem's asking for, it's asking for the area of the original index card. That is the area before Daniel snaps those two squares out from it, right? The original index card, before he snaps out those two squares. That's the key of this word here, original. So it's not 16. We don't subtract 2. The answer is 18. Okay, this is AMC 10A problem 11. Ted mistakenly wrote 2 to the m times the square root of 1/4096. And he accidentally saw this m here and was like, oh, that must be the mth root of 1/4096. You know, it happens. You make a mistake like this. But we're looking at the situation where Ted gets lucky and these two are equal. So making this mistake doesn't change his answer. Basically, that's the whole point of this problem, right? So the question is, what two real numbers m makes Ted lucky where he doesn't accidentally get the wrong answer, basically. So, well, we can simplify what we can. Let's just set these equal to each other and write in this product, right? So this is 2 to the m times the square root of 1 over 4096. And one thing to keep in mind is that if you just multiply 4096 by itself, like if you just divide 2 from it a lot of times, you'll figure out that its prime factorization is just 2 to the 12. So that's very helpful because that implies that this is 1 over 2 to the 6. So this is 2 to the m times 1 over 2 to the 6. But it's, yeah, because of the square root, it makes it 1 over 2 to the 6. But we also know that this is equal to 2 to the negative 6, right? Because the reciprocal negates the exponent. So this is just 2 to the m times 2 to the negative 6. Okay, what about this side? This is 2, and then it's times the mth root of 1 over 4096. Well, 4096, like we've already talked about, is 2 to the negative 12, right? And we're putting that to the mth root. But the same thing as the mth root, the same thing as the mth root is the 1 over mth power. These are the same thing. So therefore, this is just 2 to the negative 12 to the power of 1 over m. Okay, so now we're getting somewhere because by exponent rules, this is 2 to the m minus 6, and using exponent rules over here, this is negative 12 over m. So this is 1 though, so we get 1 minus 12 over m. And then if we take the log base 2 of both sides, we just get this. And now this is just a quadratic we can solve. We just multiply both sides by m. Therefore, m can be either 3 or 4. And the sum of all the numbers m for which these two expressions have the same value is 3 plus 4 is 7. All right. Okay, this is AMC 10A problem 12, which is also 12A problem 9. On Halloween, 31 children walked into the principal's office asking for candy. They can be classified into 3 types. Some always lie, some always tell the truth, and some alternately lie and tell the truth. The alternators arbitrarily choose their first response, either a lie or the truth, but each subsequent statement has the opposite truth value from its predecessor. So basically, the first time they answer, it could be a truth, and then they would lie and then tell the truth, lie, tell the truth, or they could start with a lie and then lie, tell the truth, lie, tell the truth, lie, tell the truth, right? So that's what the alternators do. Okay, so the principal asked everyone the same 3 questions in this order. So we asked everyone, are you a truth teller? The principal gave a piece of candy to each of the 22 children who answered yes. Are you an alternator? The principal gave a piece of candy to each of the 15 children who answered yes. Are you a liar? The principal gave a piece of candy to each of the 9 children who answered yes. How many pieces of candy in all did the principal give to the children who always tell the truth? Okay, so this can be a lot to take in. This is the longest question on the exam by far. So it can be easy to get lost in all the words. But essentially what this is aside from a math problem, this isn't very much of a math problem. This is actually more of a logic puzzle. So we have to think about how we can categorize the children, right? We have to think about how we can categorize them so that we can express we can express 22 as a sum of like, oh, this group of children said yes. This group of children also said yes. This group of children also said yes. So I'll explain what the thinking is. Basically, we divide them into 4 groups. The children who are truth tellers, the ones that always tell the truth. The liars, who always tell the lie. I'm marking it with F here because F stands for false. So they're saying false statements. Okay. But yeah, the hard part about this problem is trying to figure out how we mark the alternators, because the alternators can choose to tell a lie or the truth at their first response. Well, let's just divide them into 2 groups. Alternators, who as their first response is a truth, and alternators who as their first response decide to lie. So basically, the truth-telling students will tell the truth, tell the truth, tell the truth, the lying students will tell a false statement, false statement, false statement. And alternating truth would tell truth and then false and then truth. And alternating false would tell false and then truth and then false. Okay, so now we are ready to set up the equations, right? Okay, so the first thing the principal asks is, are you a truth teller? And apparently 22 children answer yes. Okay, well, who would answer yes to that question? Well, the truth tellers would, because they're truth tellers, and truth tellers tell the truth. So they tell the truth that they always tell the truth, and they'd say yes. The liars would also tell the truth here. I mean, they wouldn't, they lie, right? And they're liars, which means they're not truth tellers, and they don't tell the truth. So they lie about being a liar. They'd instead say, yes, I am a truth teller, even though they're not, because they're liars. And then alternating truth is actually the only one who's going to say no, because they aren't truth tellers, but they're still going to tell the truth, right? So they're alternators, and they're on this phase, right? They're telling the truth here, right? Because they start by telling the truth. Those are ATs, right? And they're going to tell the truth that, no, I am not a truth teller. I'm an alternator. So those aren't going to be included in the sum. However, the alternating ones who start by with a false statement are also going to be included for the same reason as the ones who are always lying, right? They aren't truth tellers, and they're going to lie. So they're going to lie and say, yes, I am a truth teller. So that sum gives us 22 children who answered yes. Okay, let's go on to the next one. Are you an alternator? And apparently 15 children answered yes. Okay, who would answer yes to this question? Well, the truth tellers wouldn't, because they are going to tell the truth. They're going to be like, no, I'm not. I'm a truth teller. What about the people who lie? Well, the children who lie, they're going to say yes, because they aren't alternators and they want to lie. So they're going to lie by saying that they are alternators. The alternating ones that tell the truth, are they? Well, the thing is, actually, because they told a truth as their first statement, now they're telling a false as their second statement. Which means that now they're going to lie, and they're going to lie about being an alternator. They're going to say, no, I'm not an alternator. So they're not going to be included in the sum. And then finally, the alternators who are lying, well, those are going to be included because, as said before, they lied as their first statement, but now they're going to tell the truth. And since they are alternators and are telling the truth now, they're going to be like, yeah, I'm an alternator. So they're included. And now we could go on to the third one, are you a liar? And it would be the same process. And after that, we would get another equation. And then we could combine that with the fact that in total, all four of these groups equal 31 to solve for all four variables. But look at what the problem's asking. It's asking for how many pieces of candy the principal gave to the children who always tell the truth. But we already know that because we just subtract these two equations. You can just subtract them. And t is just 22 minus 15 is 7. Okay, this is AMC 10A problem 13. Let ABC be a scalene triangle. Point P lies on BC so that AP bisects angle BAC. The line through B perpendicular to AP intersects the line through A parallel to BC at point D. Suppose BP equals 2 and PC equals 3. What is AD? Okay, so let's try to draw this figure. I'm going to try to draw the figure as to scale as I can. There we go. So here is our triangle ABC. And the reason why I didn't draw it taking up the whole screen is because, as we're about to see, point D is going to be right around here. So if we draw the angle bisector of A, it's going to intersect here at P. And BP is 2, PC is 3. Well, now we're looking at the line through B perpendicular to AP. And we are intersecting that with the line through A parallel to BC. So let's draw some parallel marks. And the angle bisector, we draw that these two angles are equal, and this perpendicular. Okay, so this is a lot to take in for this problem. So the question is, where do we start? Okay, we need to clarify two things for this problem. The first is a theorem called the angle bisector theorem. The angle bisector theorem basically states that if we have the angle bisector in a triangle, right? And let's say we call this W, X, Y, and Z, then W over X is equal to Y over Z. In other words, these two ratios are equal if and only if this is an angle bisector. Okay. So how does this help here? Well, we can apply the angle bisector to this problem directly because we have an angle bisector and we have a ratio, which means that by the angle bisector theorem, this has to be 2 times some constant k, and this whole length here has to be 3 times some constant k. Okay, so now we're making progress because we have another ratio to work with, and actually we can make even more progress because AB, and now let's call this intersection point here, let's call it E. Oops, let's call this intersection point E. Well, we know that ABE is an isosceles triangle because these two angles are equal where there's a perpendicular, right? In other words, these two triangles are congruent. So we're putting two congruent triangles back to back, which gives us an isosceles triangle. And the reason why that's important is because we know that this length here is equal to 2k. And therefore, this length equals k in order to make the full length 3k. All right. And now we are at the end of the problem. And now there's one more thing that needs to be seen here in order to solve the problem, which is similar triangles, basically. In particular, this type of similar triangle is called bow tie. So what bow tie is basically if we have two parallel lines, two parallel segments, and we connect their endpoints in this fashion, these two triangles have to be similar to each other, which makes sense, right? Because these are alternate interior angles of the parallel lines, right? And these are also alternate interior angles. And bam, by AA similarity, these two triangles are similar. Okay, well, now, once I point this out, right, it might have not been so obvious at first, but now it's probably very obvious here that AEC and BED are similar in this sort of way. They're similar in this sort of bow tie fashion, right, with these parallel lines. And the reason why that's important is because they're parallel in a way such that the ratio of BC to AD is simply the ratio of CE to EA. But we know that the ratio of CE to EA is just 1/2. So therefore, AD is just 2 times BC. And since we know the value of BC is 5, then it's just 10 and we're done. Okay, this is AMC 10A, problem 14. It is also AMC 12A, problem 10. How many ways are there to split the integers 1 through 14 into 7 pairs so that in each pair, the greater number is at least 2 times the lesser number? So I'll just give some examples. For example, 4 and 9 works. 5 and 12 works. What doesn't work? Well, 3 and 5, for example. This doesn't work because, well, 5 is not at least 2 times 3, right? 5 is not at least 6. That is not true. So the question is, how do we approach this problem? Because if we just try to list out the solutions, we are going to run into a dead end very quickly. But the key thing here to notice is that while, for example, the number 1 can be paired with literally any number. It can be paired with any number from 2 to 14, right? Which isn't very helpful, right? So for example, we shouldn't start by pairing 1 to one of the numbers. That is not a good idea. What we should start with instead is the higher numbers. based in what I mean is the numbers 8 and higher. The numbers 8 and higher, 8, 9, all the way up to 14, because those numbers have to have numbers smaller than them, which really reduces the number of numbers, right? So let's try that. Let's start with 8. For example, 8, we can't have any of the numbers 9 through 14 pair with it because they're all greater than 8, but they're not at least 2 times 8 because 2 times 8 is 16, which is greater than 14. So it can only be paired with 1, 2, 3, and 4. And then if we go on to 9, we actually see the same thing happens, 1, 2, 3, and 4, because 5 is too big. 5 times 2 is 10, which is greater than 9. And if we list this out, we see that 10 can be paired with 1, 2, 3, 4, or 5. 11 can be paired with 1, 2, 3, 4, or 5. 12, I'll just write it over here. 12 can be paired with 1, 2, 3, 4, 5, or 6. 13 can be paired with 1, 2, 3, 4, 5, or 6. And 14 can be paired with 1, 2, 3, 4, 5, 6, 7. Okay, but why is this useful? Well, hopefully you can see that this is extremely useful. In fact, we can just solve the problem now because this shows us that 8, 9, 10, 11, 12, 13, and 14, they all have to pair with the numbers from 1 to 7. So we can just start by pairing 8 to one of the numbers, then pair 9 to one of the numbers, 10 to one of the numbers, and go up till we pair 14 to one of the numbers. And we can just count the number of ways to do that and we'll be done. And this is actually, if we start with 8, it gives us the easiest process and you'll immediately see why. For 8, how many ways are there to choose the number we pair it with? Well, 4, right? Obviously, we can choose 1, 2, 3, or 4. How many ways are there to do it with 9 after we choose 8? Well, there's 3 ways, right? Because let's say we choose 3. Well, no matter what number we choose, it's going to also be here, right? Because they pair with the exact same numbers. So once we pair with 3, for example, 3 will be gone from all of these, right? We can't pair 3 with any of the others. Okay, well, now let's say that with 9, we choose 1, right? That's the number we pick. Oops. Okay, well then we can't pick 1 for any of these numbers. How many ways are there to do 10 now? Well, there's 3, right? And there was no other way for it to not be 3, right? Because no matter what 2 numbers we pick for 8 and 9, those 2 numbers we pair them with is from 1 to 4. And 10 covers all the numbers from 1 to 5, which means that it'll cover those 2 numbers. And that's the really cool thing, right? 1, 2, 3, 4 is a subset of 1, 2, 3, 4 is a subset. And that's what finishes off this problem, basically, because all the numbers we choose from previous will affect the next one always, which allows us for a consistent way to count, right? So for example, for 10, let's say we pick 5, right? None of these numbers can have 5 anymore. Okay, what about 11? Well, now there's only 2 choices, 2 or 4. Let's say we pick 2. Okay, well, now we move on to 12. How many possibilities are there? Well, none of these and not this one, 4 or 6. There's only 2 possibilities. Let's say we pick 6. Okay, now 6 can't be done here, 6 can't be done here. Well, now 13 only has 1 possibility, and 14 only has 1 possibility. So this just gives us the product we need. 4 times 3 times 3 times 2 times 2 times 1 times 1. It follows this nice pattern that makes a lot of sense, actually, which is that each time we go down, well, every other 2, it goes down by 1, right? Which makes sense. And this is the product we need. 4 times 3 times 3 times 2 times 2 times 1 times. And this just product equals 144. Okay, this is problem 15 of the AMC 10A. Quadrilateral ABCD with side lengths AB equals 7, BC equals 24, CD equals 20, and DA equals 15 are inscribed in a circle. The area interior to the circle but exterior to the quadrilateral can be written in the form A pi minus B over C, where A, B, and C are positive integers such that A and C have no common prime factor. What is A plus B plus C? A, 260, B, 855. C 1235, D 1565, E 1997. Okay, so these are all very the reason why I read them is because these are all very large numbers, right? Because we're going to get a fraction with very large numbers. This is actually going to be a pretty ugly solution, but anyways, this is going to be a quick problem if you know your Pythagorean triples. If it's not, then you're probably not going to be able to solve it because it's a lot harder without Pythagorean triples, or just, although the other way you could do it is, well, if you know what Pythagorean triples are, chances are you probably already know how to solve this. But if you don't know what they are, the other way you can see how to solve this is by drawing an accurate diagram. If you draw an accurate diagram in the test, right, you'll notice that ABC and ADC seem like right angles. They seem like right angles. And well, AC looks like a diameter of the circle. And if you look for a little bit and you realize that 724, that this is true, 7 squared plus 24 squared is 25 squared, and that 15 squared plus 20 squared equals 25 squared, then you will realize that this diameter has to be 25. It has to be diameter and it has to be 25, and these are right angles. So basically, the entirety of this problem relies on finding the fact that AC is a diameter by figuring out that AB squared plus BC squared equals CD squared plus DA squared. That is actually a very common technique in problems like this, where they give you a quadrilateral inside a circle. Chances are one of the 2 points forms a diameter, and that can help you solve the problem. And now from here, it's not too difficult to solve because the area of the circle, well, that's just pi times 25 over 2 squared, right? Because our radius is 25 over 2. And then we have to subtract the area of the quadrilateral, which is 7 times 24 over 2 plus 15 times 20 over 2. And we can just put that all over 2. Right. So now we just get over here, 625 pi over 4 minus, and then over here we get 7 times 12, which is 84, and then minus 15 times 20 over 2, which is 150, which this just gives us minus 234. And now we just have to multiply 234 times 4 to get it onto the fraction. And this is why the problem gives you such large values, right? That makes sense why the answers are so large, because you have to add up very large numbers, basically. And if we multiply that out, we get 936, which means that our final answer is 625 pi minus 936 over 4. Yep. Yeah, okay, that's good, I think. And basically, at this point, we get our numbers A, B, and C. A and C have no common prime factor. That's good. Okay, and now we just find A plus B plus C, which is 625 plus 936 plus 4, which gives us the giant number 1,565, which is choice D.